Hello, students. So, what we've just introduced is the idea of convergence of sequences of functions in the pointwise sense and in the uniform sense. Let's recall those definitions. So, we say that a sequence of functions, f sub n, converges pointwise to some limiting function f on the domain U if, well, I'll give two different versions of this definition. For all, x in U, f sub n of x, which is now a sequence of numbers, right? You plug an element x into the sequence f sub n, you get a number. So this is a sequence of real numbers. So we know what it means for that to converge. Converges to f of x. So just for each input, the sequence of outputs converges. That's what pointwise convergence means. For each point in the domain, the sequence you get from plugging in that point converges. Alternately, we have a definition of this. So let's just expand that definition. For all x in U, for all epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N, absolute value of f sub n of x minus f of x is less than epsilon. And as we've seen an awful lot in this class, the way that you declare quantifiers matters an awful lot. So what can that big N depend on? Well, it can depend on the choice of epsilon, which you expect. The closer you want the limiting function to be the closer you want the sequence of functions to be to the limit, the farther out in the sequence you have to go. So you expect a smaller choice of epsilon to result in a bigger choice of n, but it also depends on the choice of x. How the sequence converges depends on where you look at the sequence. So, as we've seen, that can result in some bad behavior, like a sequence of continuous functions converging to a limiting function which is not continuous. So we're going to we introduced another notion of convergence with the aim of fixing that. So we say that a sequence, I don't want that color, f sub n converges uniformly to f on U if, well, all that gets changed is I want this n to not depend on x. So how do I arrange that? Well, I declare x after big N. For every epsilon greater than 0, there exists a choice of big N such that for all x in U, and for all little n bigger than big N, absolute value of f sub n of x minus f of x is less than epsilon. Our goal in this lecture is to show that uniformly convergent sequences of functions have the nice properties that pointwise limits of sequences of functions don't have. So, here's the first main goal of this lecture, Theorem 4.2.1. Suppose that f sub n from U to R is a sequence of functions. Let f be the uniform limit of f sub n. Then f is continuous on the domain U. So a uniform limit of a sequence of continuous functions is continuous. That is not true for pointwise limits. Before we give the formal proof, let's give a sketch of the proof. And I'll make reference to this figure and explain it as we go. So the fact that f sub n converges to f uniformly means that by taking n big enough, I can get f sub n of x minus f of x to be less than epsilon for every x in U. So what does that mean graphically? That means that for absolutely every input, the difference between f of x, f sub n of x, so there's f sub n of x, and f of x is less than epsilon. So f of x has to live somewhere within that little tube of height 2 epsilon. So any xy value on the graph of f of x has to lie inside of that dashed tube. All right. Well, f sub n is continuous, So that means that I can make f sub n of x minus f sub n of p as small as I want by taking x close enough to p. So that means that since there's f sub n of p, and there's f sub n of x, I can arrange by making that distance less than delta, I can get this height to be less than epsilon. But remember, I also know that f sub n of p and f of p are within an epsilon of each other. So that means that this vertical distance between f sub n of p and f of p, maybe f of p is right there, that difference is less than epsilon. The difference between f sub n of x and f of x, that difference is less than epsilon. So what's the greatest that this vertical difference between f sub n of x and f sub n of p can be? Well, it could be epsilon plus epsilon plus epsilon, assuming that they all point in the same direction. So that's 3 epsilon, but I could divide all these epsilons by 3, and that would give me the proof. So saying that now in one, since f sub n is continuous, I can make f sub n of x minus f sub n of p less than epsilon by taking x and p close enough to each other. So the resulting... So let's summarize what was in that picture. So if I take those two inputs, are the y values, f of p and f of p and f of x, close to each other? Yeah, they are. They are within 3 epsilon of each other, and we can see that by a triangle inequality. In fact, let's see that triangle inequality argument as right now. Well, so when you use the triangle inequality, right, you want to find successive things that are close to the things you have and are somehow close to each other. So in order to estimate the distance from f of x to f of p, well, I'll realize that as being the same thing as f of x, which I know is close to f sub n of x, plus f sub n of x. F sub n of x, according to this picture, that y value is f sub n of x, is close to f sub... No, that was f sub n of p. F sub n of x up here is close to f sub n of p. So I'll subtract and add f sub n of p minus f sub n of p plus f sub n of p, and then minus f of p, because that was one of the terms in the expression I was interested in originally. And now I'm set up to use the triangle inequality. That is now less than or equal to absolute value of f of x minus f sub n of x plus absolute value of f sub n of x minus f sub n of p plus absolute value of f sub n of p minus f of p. And let's just take a look at that. This will be less than epsilon, because little n is bigger than big N, plus epsilon, let's make that one blue, plus epsilon, because absolute value of x minus p is less than delta, plus epsilon, again because little n is bigger than some choice of big N that we make. Oh hey, that's 3 epsilon? That's not the same as epsilon, but we know how to deal with that problem. We're just going to divide our epsilons by 2. So now that we've seen a sketch of the proof, let's actually do the proof. Proof of theorem 4.2.1. Suppose that f sub n from U to R is a sequence of continuous functions. Let f be the uniform limit of f sub n. Now consider any p in U. I have to show that f is continuous at p. So you'll notice that the first thing that we did in the sketch of proof is we built that little tube that all of that f of x has to live within. It's going to be close to f sub n. So let's do that first. Consider any epsilon bigger than 0. There exists some big N such that for a little n bigger than big N and all u in big U, the absolute value of f sub n of u minus f of u is less than epsilon over 3. And here's something that I want to emphasize. This inequality is independent of u. This choice of big N is independent of u. So as long as little n is bigger than big N, then no matter what input I use, maybe x, maybe p, I haven't declared x yet, of course, I will get that resulting inequality. All right, so now let's consider a little n bigger than big N so that that green inequality holds. Let's underline the whole thing, the green inequality. So I'll now fix some little n bigger than big N. I know that f sub n is continuous, right? That's one of the assumptions of the theorem. So f sub n is continuous at p in particular, the place where I'm looking. So there is some delta bigger than 0. And let's just think about what this delta depends on. So this depends on epsilon, which is fine. It depends on p, which is fine. It depends on n also, though. And that seems maybe a little bit suspicious. But let's convince ourselves that it's not suspicious. So let's think about that little n. That little n is something that depends on big N, because it has to be something bigger than big N. That's the only constraint it has. Big N depends on epsilon, only on epsilon. So what can we deduce from that? We can deduce that little n really depends only on epsilon. So this delta really depends only on epsilon and p, which is good. All right, so fix some little n and big N. Since f sub n is continuous at p, there exists some delta bigger than 0, so that for every x in u, if the distance between x and p is less than delta, then the distance from f sub n of x and f sub n of p is less than epsilon over 3. All right, cool. So what have we done so far? We considered any epsilon bigger than 0. We did some jiggery-pokery, and we cooked up a choice of delta bigger than 0. Now I have to consider any other x in the domain and assume that the difference between x and the place where I'm checking for continuity is less than delta. I will do so by using the triangle inequality. This step is going to look an awful lot like this step. So I'll just spread all of that stuff out over 3 lines, but I'll write almost the exact same thing. Okay, let's do it. So the difference between f sub n of x, f of x, and f of p is equal to f of x minus f sub n of x plus f sub n of x minus f sub n of p plus f sub n of p minus f of p. And right, there are always 2 things that you should ask. Is this something we can do, and is this something we should do? So if you're just reading the proof as we're going, everything is certainly something that we can do. It's not so clear why it's something that we should do, but we went and did the sketch of proof above, so we know that this should work out. By the triangle inequality, this is less than or equal to f of x minus f sub n of x plus f sub n of x minus f sub n of p plus absolute value of f sub n of p minus f of p. And that's less than epsilon over 3 by this plus epsilon over 3. This is less than epsilon over 3 by this, plus epsilon over 3 by this line again. And that all adds up to epsilon. So what have we done here? We've shown that for every p in u, and any epsilon bigger than 0, there exists a delta bigger than 0, such that if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. F is continuous at p. Since that's true for every p in u, f is continuous on all of u. So I'm going to break the video right here. Let me tell you what my next goal is. So the next thing that we observed in the previous lecture is that if you have a sequence of pointwise converging functions, and you want to interchange the order of limits, you want to compare the limit as n goes to infinity of the limit as x goes to c of f sub n of x with the limit as x goes to c of the limit as n goes to infinity of f sub n of x. These two are not the same if you have pointwise convergence. Our next goal is to prove that that does happen if we have uniform convergence. So I'll stop the video right here. I'll talk to you in just a second. Ciao.